Hi, Math 12. This is our second lesson on the transformations um, unit. So we just finished looking at um, translations, which was the movement of a function horizontally or vertically. And so now what we're going to look at is reflections and stretches. Eventually what we'll do is we'll combine all of these together. So a reflection is essentially what it sounds like. It's sort of the reflected function is a new image that's created on some line of reflection. Okay, so think of this sort of as a mirror line, and that mirror line can either be vertical or it can be horizontal. And now when this happens, one of the points remains unchanged, and that's called an invariant point. Okay, so an invariant point is basically a coordinate that both the original function and the reflected function share. Okay, so it's the same in both. Now it depends where the mirror line is for that to be the case. So like this first one here, there is no invariant point. Okay, so what we have here is the original function fx, and here is what we call negative fx. Okay, so this is reflected, and it's reflected along the x-axis. Okay, so notice how the negative is in front of the function. Okay, the other option is where you have the negative placed inside, going with the x like that. So here, instead of being reflected along the x-axis, this is going to be reflected on the y-axis. Okay, so let's look at a couple examples here. Okay, so start with this one. So here's the original function. Okay, so we can call this fx. And so what we want to do now is we want to try to find the two reflected functions. So first off, we'll do negative fx, and then we'll do f of negative x. Okay, so those are the two we're gonna draw. So let's start with some coordinates that we can get off of this one here. So doesn't matter which ones here. So let's say we look at this one, and this one. Okay, so just taking three coordinates. Again, doesn't matter where you have them. So let's call this fx. And the three coordinates I've got are 2, 8, 0, 4, and I've got negative 2, 0. Okay, so let's do, I'll change colors here. Let's look at a negative f of x. Okay, so what this means is we're going to keep the x values the same. Okay, so 2, 0, negative 2. And what we're going to do is we're going to multiply the y value by negative 1. So this is going to become negative 8, negative 4, and that's going to just be 0. Okay, so let's draw this up now. So we've got 2, negative 8, 0, negative 4, and negative 2, 0. Okay, so that would be these two here. This would be your invariant point. Okay, because they both share that. Okay, so here's your reflected negative f of x. Okay, and so where this one is being reflected is the mirror line here is going to be x equals negative 2. Okay, so that's where the image is being reflected. Okay, let's look at another one here. y equals f of negative x. So now what you do, so I'll just put the ones we started with again. Okay, so let's look at f of x. Okay, so that was 2, 8, 0, 4, and negative 2, 0. And so this is going to be f of negative x. Okay, so now what's going to happen here is you keep the y exactly as they were. Okay, and now what happens is you multiply the x by negative 1. So this is going to be negative 2. That's going to stay 0, and this is going to be positive 2. Okay, so we've got negative 2, 8, 0, 4, and 2, 0. Okay, and so here's your f of negative x. Okay, and so the invariant point here is going to be 0, 4. Okay, so there's your invariant point, and this function is going to be reflected upon the y-axis, right? Because that's where the so again, the reflection line is kind of where your mirror would be, and that gives you the reflected function. Now, so this is looking at reflection. The other thing that we can do is we can talk about stretching functions, or so that would be a stretch would consist of either an expansion or a compression. So how this would work is either a multiplication in front of the function or a multiplication of the x value. So that's what you see at the top here. Okay, so a would be the multiplier in that instance where you're multiplying in front of the function, and then b would be where the x value is being multiplied. So here's an example where you've got your base function. Okay, so this would be fx right here, y equals x squared. So that's your base function. And so what's happening here is if in both of these instances, here you've got b equals 2, and here you got b equal to 0.5. Okay, and so what you'd notice that's happening here is for the one that's b equals 0.5, this one is going to be a horizontal stretch or a horizontal expansion. Okay, so you can think of that as an expansion. And then for the one that has 2x, you've got a horizontal compression, right? So which means it's being squished in horizontally. Okay, so that's one instance. The second one is the a value, which is multiplied in front of the function. So again, here's your base function fx. So here you're saying a equals 2, and here you're saying a equals 0.5. And so what's happening for a equals 2, it's a vertical stretch, and then for a equals 0.5, it's a vertical compression. Okay, so it's basically getting squished down. Okay, and so to figure out the functions here, there's a little part here that's kind of tricky, which we'll get to. But let's start with let's look at that through this example here. So we've got y equals fx. Okay, so that's the one that's given to us. Okay, so this is fx. And so we want to draw 4 different types of graphs on the same grid that are basically transformations of this fx function. So the first thing we can do is, again, we can use the mapping technique where you take the original coordinates of the function and you come up with the image points. So let's take these 3 coordinates right here. Okay, so we've got okay, so going left to right, we've got 0, 3. Okay, we've got 3, 6. And we've got 6, 0. So let's start with gx. Okay, so gx. So gx is basically saying f of 2x. Okay, so what this means is you keep your y values the same as they are here. So 3, 6, and 0. Okay, so this is kind of the tricky part. So you notice how it's 2x. So that's not a multiplier. That actually what happens is it takes your x value and it divides it by 2. So now this is going to be 0, 1.5, and 3. Okay, so that's the part here you have to be aware of for this type of function. Okay, so now if we do the new function, you've got 0, 3. Okay, so that would be your invariant point. And then you've got 1.5 and 6, so that would be up there, and then you've got 3, 0, which would be right here. Okay, so that would be your g of x. Okay, so just be aware of that. That multiplier of 2 means that you're dividing by 2. Okay, let's look at the next one here, h of x. Okay, so h of x. Okay, so h of x is, you see how the multiplication of 2 is in front. So what happens here is your x values now stay the same. Okay, so 0, 3, 6. And what happens is your y values are going to be multiplied by 2. So here you're going to get 6, 12, and 0. Okay, so you've got 0, 6. Okay, so 0, 6. And you've got 3, 12. Okay, so 3, 12 kind of goes beyond the grid here, so that's up here. And then you've got 6, 0. Okay, so 6, 0 here, this would be your invariant point. Okay, and so here's, okay, so this would be your hx. Okay, okay, let's do the other two, lx, or yeah, lx there. Okay, so lx, what's going on is we're going to do the same thing, except this time we're going to multiply the function by a half. So again, you keep the x values as is, 0, 3, 6. So again, this is looking at the original function f of x. And then what you do with the y values is you're going to divide those by 2. So 1.5, 3, and 0. Okay, so you get 0, 1.5, 3, 3, and then 6, 0. Okay, so 6, 0 here is your invariant point. Okay, and so that's Lx. Okay, and the last one here, Mx. Okay, so Mx. Okay, so Mx, what's going on here is we're going to, the multiplier is 1/2 in front of the x. So again, you do the opposite. Instead of dividing by 2, we're going to multiply by 2. So again, this has to do with the x values. So the y values stay the same, so 3, 6, 0. Okay, and then we multiply the x values by 2, so we get 0, 6, and 12. Okay, so again, just like with the gx function, notice that we're doing the opposite in terms of what goes on with the x. Okay, so that's the important point here. Otherwise, you're going to get a bit confused. So 0, 3, so that would be our invariant point. Okay, and then we've got 6, 6. And then we've got 12, 0. So again, around here somewhere. Okay, so this will be your mx. Okay. Now notice how it also says to, so I've mentioned the invariant points already. It also says to give you the domain and range. So just recall, domain is your possible set of x values, and your range is the set of y values. Okay, so let's just, I won't do it for all four of these, but let's say we took, let's say we took the, let's do the function for, let's do the function for, let's do f of x, okay? Just because that's the one we started with. So if I were to do f of x, okay, so there's the coordinates for f of x. So what I would say here is that your domain, so I'll use the proper notation here. The domain would consist of the set of x values between 0 and less than and equal to 6. Okay, where x is inclusive of all real numbers. Okay, and your range here would be the y values, which would be between 0 and less than and equal to 3. Oh, sorry, that would be 6 as well. Or y is inclusive of all real numbers. Okay. So remember, when you're doing the domain and range, this is what we use when we have sort of a confined set of values. If you have a function, let's just go back here, like these ones here, where they just keep going forever, then you can say that it would just be all real numbers, okay? Because it keeps getting higher and lower, and it keeps going left and right. With the parabolas here, the x values would consist of all real numbers because it keeps getting more left and more right. The y would be greater than and equal to 0. Okay, so it keeps going up. So 0 for y would be your minimum value. Okay, so I'll stop there. So now we've looked at translation, which again is moving horizontally or vertically, the function. We've looked at reflection, which is sort of a mirror image along the line of reflection. And now we've looked at stretches, which are either horizontal or vertical, and they can either be expansions or compressions. Okay, so we're, like I said, at this, for this first part here, we'll look at these transformations individually, but like I said, we'll be combining all of those together. Okay, so it's really important that you understand them individually before we kind of combine them and have a function that has more than one transformation applied. Okay, so I'll stop here, and you can work on the indicated questions now.